Hello and welcome to this video where I will teach you the basic concepts in the topic force. And we want to review a little bit about physical quantities. We have already learned that a physical quantity is the feature of an item which can be measured. And there are two types of physical quantities. Basic physical quantities, there are 7, and then we've got very many derived physical quantities. Now the difference between basic physical quantities and derived physical quantities is that while basic physical quantities cannot be obtained from any other physical quantities, you find that derived physical quantities are actually obtained from other physical quantities by the process of multiplication and division. Force is a physical quantity. It is a derived physical quantity. So we want to ask ourselves, what is force? I know somewhere you may have encountered this fact that a force, okay, we are talking about force. Let me just write it here so that we can know exactly what we are dealing with. Force. You have learned somewhere that if you've got an object here, you either push, this one is a push, or you pull, this object is going to move if it was stationary. And if it was moving, it can either move faster or even slow down depending on the direction in which you apply this force. If you apply the force in such a way that it acts in the same direction as the direction in which the object is moving, then the object is going to move faster. If you apply it at an angle, it can change the direction in which the object is moving. If you apply it in the opposite direction to the direction in which the object is moving, the object is going to slow down, as it happens in the braking system of a car. So, this push or pull is what we refer to as a force. In many textbooks, you'll find that, or you may even have been told, that a force is defined as a push or a pull. That is just a description of what a force is. Because to define a physical quantity means to show how it is obtained from other physical quantities by either multiplication or division, because force is a derived physical quantity. But when we put the words push or pull, we cannot associate those words with any equation. So the proper definition of force will come later when you've been introduced to other physical quantities, and then we will define force in terms of momentum and say that force is the rate of change of momentum. But because at this level you probably don't have an idea of what momentum is, then we will put it on hold. Then why are we going to a physical quantity and we have not covered other physical quantities which are required to define it? Because the process of physics is such that when you define a physical quantity in terms of other physical quantities, that you show that when, for example, let me just give you an example of density. Density of a substance is given by the ratio of its mass to its volume. You see, the moment I define density as mass per unit volume, or the ratio of its mass to its volume, then there is an equation which stems directly from that definition. For me to define density, or for me to start talking about density, I must have talked about mass and volume. And indeed, you find that mass is a basic physical quantity, volume is a derived physical quantity. It is derived from length. When you multiply the length 3 times, and these lengths are mutually perpendicular to each other, as it happens in the case of a cuboid. There's a cuboid. It's got some height, it's got some length, it's got some width. When you multiply that, length, width, and height, you get the volume. So before we talk about density, we have already talked about these two, so that when now we talk about density, we are defining it in terms of physical quantities which we have already encountered. It is not the case with force at this particular level, because at this level we are saying that the proper definition of force is rate of change of momentum. The reason why we find it necessary to teach you about force at the very beginning is because other very simple concepts are obtained from force. Before we can start talking about momentum, which is in Newton's laws of motion, at that time is quite large if we are not, for us to have failed to talk about force. And besides, force is a physical quantity that you've talked about in your primary school. So there is no harm in saying that it is either a push, or a pull. But remember, that is only a description of what a force is. It is not a definition. Just remember that. You will encounter the definition later on. Now, force is measured. Now we talk about the SI units of force. So we can put force there. It can be lowercase letters, uppercase. It really does not matter. Force is measured in newtons. Newtons. These are the SI units of force, newtons. The abbreviation of Newton, or the short form of Newton, is N. For example, if I'm talking about a force, the force that I'm applying here, I can say that that force is 200 newtons. A physical quantity usually, the magnitude of the physical quantity usually has a number and a unit. Now, it would be wrong to write this number here as, okay, I'm going to write it down here, but remember, this is not correct. That is not correct. So let me immediately put an X here. It's not correct to write it that way. I'm going to explain in a moment why that is not correct. The other wrong way of writing this is to write 200 and then you say this. Again, this is not correct. The correct way of writing it is like this, or you just write 200. If you want to use lowercase, then it's got to be the complete word, newtons, like that. Now, why is it like this? SI units, which are names of scientists who have contributed a lot in the development of that concept, usually follow a certain pattern when it comes to stating the units. These units, there are many in physics, so it is important to know how to write them. First of all, how do you identify them? Majority of these units are not among the 7 basic physical quantities. In fact, there is only one of them which is the name of a person, and this is ampere. Ampere. The rest are not names of people. And I've already explained that when you write ampere, a current, maybe let's say 2 amperes, you write uppercase A. And if you've got to write the complete word, then that word or that name has got to start with lowercase. Very important. That only applies to units, SI units, which are names of people. So it is very important to get this one straight. So let's look at the effects of a force. This question usually pops up. So a force can affect the motion of an object. For instance, if an object was stationary and you apply a force, it can start to move. If it was already in motion and you apply a force such that you are pushing the same object which is in motion and you are pushing in the direction in which the object is moving, then you find that that object can accelerate. In other words, it can move faster and faster. But if you are pushing this object trying to oppose its motion, it will slow down and probably even stop. And if you are pushing it at an angle, it is moving to the right like this, but then I'm pushing it in this plane, then it's going to change direction. So there are very many effects of a force as far as the motion of an object is concerned. This is studied later on in a topic we call Newton's laws of motion, later on. And that is where we are going to encounter the proper definition of force. Forces can also change the shape of an object. For example, if you get a spring, you are able to apply a force and you're going to distort. You're going to either make it longer, and if it was something like a balloon, for example, you can squash it so that its size becomes smaller. So you see, it can distort, change the shape of an object, or even change its size. This is studied a little bit more in a topic we call Hooke's law, where we look at specifically the extension of an object, such as a spring or a string or even a wire, when forces are applied to it. So you can see topics in physics, they are like effects of a force. In fact, there is another one which you're going to study in Form 2 called turning effect of a force. If you want to open a door, you definitely have to push it at the handle. When you push it at the handle, then that door is going to turn. It's going to turn about a point. And that topic is called the turning effect of a force. The next topic after this is also an effect of a force. So, forces can also exert pressure. And when you divide the force applied by the area of contact, pressure is exerted. So you can see a full topic on effect of a force. Forces can also do work. All these are effects of a force that you can mention in the exam when you are asked to state effects of a force. In most cases, when students are asked to state effects of a force, they only mention those effects which deal with motion, but they forget that there are so many other effects of forces. Forces can also do work in a topic we call work, energy, power and machine, somewhere in Form 3. So we are going to deal a little bit more on each one of these effects as a full topic. But for now, it's just enough when we say that forces can change the motion of an object, can exert pressure, can do work, and so forth as separate points, which are going to earn you marks when you're asked to state effects of a force. Now, when we are still at this point, let's look at how forces are represented on a diagram, for example. And here I'm going to use a grid. And let me just see. Let's assume that there is an object here. This one is the object. It may be a block of wood, a brick on a surface, and it is in contact with the surface here. And you're going to apply a force here. You tie it with a rope, and then you pull or you push by physically getting hold of it and pushing. So you can apply a force to the right like this. You can also apply a force in the same direction, but a smaller amount of force. So the length of this arrow represents the amount of force that you are applying, the magnitude of the force. And the arrowhead shows the direction in which you apply the force. So a force is represented by, first of all, a line segment. You draw a line segment like that, or a line. And then we attach an arrow to that line showing the direction in which the force is acting. Later on in this topic, we are going to look at the vector nature of a force, where we are going to say that it's a vector, and a vector is a physical quantity with both direction and magnitude. Magnitude just means size, and the size is represented with a number. Like, for example, I can say 1, 2, 3, 4, 5, 6. I can say this is 6 newtons. It is represented by a number and a unit. This is the magnitude of the force. Okay, and then this is the direction. Here I'm saying let one division here represent 1 newton. So a force acting in the same direction but having half the magnitude of 3 newtons would occupy 3 centimeters like this, or 3 divisions. If it's acting in the opposite direction like this, and maybe it has a different magnitude, occupies 4 spaces, then it is 4 newtons. So you can see these forces are different, and 2 of them are similar in one way but different in another one. For instance, this force and this force, they are similar in the sense that they are acting in the same direction. Look at the arrow, both of them are pointing to the right. So they are similar in that sense. But they are different when it comes to the size. This one has a smaller magnitude compared to this. This 4 Newton force is different from these two in both ways. It's acting in a different direction, and it has got a different magnitude. So when you're talking about forces, you can distinguish the forces in terms of, okay, is it a push or a pull? You can also think about what type of force is it? Because there are so many types of forces. Or you can think about what is the direction of the force? What is the magnitude of the force? You know, so all these are different ways of distinguishing between one force and the other. So remember, a force is represented by a line segment with an arrowhead. Now let's look at a summary of these points that we've talked about. So here I've got the points. What is a force? I've avoided using the word definition, and I've explained to you why I have avoided using the word definition. Because in physics, if you're to define something, it will be accompanied by an equation, and we've not come to a point where we can attach an equation that is associated with the definition of the force at this particular moment. So what I've given here is that is just a description. But if in the exam the teacher just asks you define force, and you are in either Form 1 or Form 2, or you have not covered that topic, which is Newton's laws of motion, just state that a force is either a push or a pull. But after covering Newton's laws of motion, and now you are asked what is the definition of force, it will not be right for you to say that it is a push or a pull. At that moment, we expect you to say that force is a rate of change of momentum. I hope that point is clear. Number 2, what is the SI unit of force? We have already said that it is Newton, and I've already explained the way it is abbreviated, and here I've given you several examples of when it is correct and when it is not correct to write it. Effects of forces. Again, we have looked at changes the way an object moves, it produces a turning effect, it exerts pressure, it does work, it changes the shape of an object. And I've already said that each one of these effects is a topic all by itself in our syllabus. Now, there is this question here: state any similarities or differences between the forces which are illustrated in this figure here. Okay, I did not finish that, but I'd like us to look at that. And here it is. And we have said when we are comparing forces, we can compare them in terms of the type of force. That is what we are going to look at in our next lecture. In terms of the size, in terms of the direction in which it is acting, or whether it is a push or a pull. If, for example, an object is given. If I draw an object at this point, let me just draw an object here. Now let's assume this is the object on which this force is being exerted. First of all, this one will be a pull. It will be a pull. But if the object is drawn in front of the arrow here, it will be a push. So let's look at the distinction or the differences between these forces. When you look at F1, it is occupying 8 squares, 8 squares like that. The other force which occupies 8 squares is F4 and even F2. I think this one is also 8 squares. 1, 2, 3, 4, 5, 6, 7, 8. So F1, F2 and F4 are similar in the sense that they've got the same magnitude, the same size. We can say each one of them is 8 newtons. 8 newtons. This one is also 8 newtons. And this is 8 newtons. We are able to draw that similarity by understanding that the length of the arrow or the length of this line segment is proportional to the magnitude of the force. And by magnitude, remember, we have said it simply means size, which is a number, 8, and a unit, newtons. But the three forces, they are different. In what way are they different? They are different in the sense that they act in different directions. They act in different directions. And so is F3. F3 is not similar to any of the forces given here. Because you can see, just by looking at the arrow, which points to the right, it's got a shorter magnitude. This one will be 4 newtons. But it is similar to F1 in the sense that both of them are pointing in the same direction. But as far as F2, F4, and F5 are concerned, F3 is different from those three, from F2, F4, and F5 in both magnitude and direction. And so is F5. So you have seen that I'm just counting the squares here. How can we be able to get the length of this line here? It's very simple. We'll just look at how many squares we have here. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 10 squares. And then vertically we've got 1, 2, 3, 4, 5, 6. And then we can just assume that we are drawing a right-angled triangle. This is a right-angled triangle. Of course, this is 90 degrees. And you can see that this one is the hypotenuse. So if we have seen that this is 10 squares, 1, 2, 3, 4, 5, 6, and this is 6 squares, we can say that F5 will be equal to 10 squared plus 6 squared. It's not 60, but 6 squared square root. Because this is how we find the hypotenuse of a right-angled triangle. This is 100, this is 36, and we can get the square root of 100 136 newtons. So you can quickly use the calculator and get that magnitude. When we come to the vector nature of force, we'll be able now to get the direction of this force, and we do that by calculating maybe this angle somewhere here, or the angle it makes from the vertical, depending on what we want. I'll show you that method when we come to that point. So in summary, we've been able to look at the meaning of force, a description of the term force, the SI unit of force, effects of a force, and we've been able to see how we represent force on a diagram using a line segment with an arrow head, which generally we refer to as an arrow. Now let's look at types of force, and we are going to start with the most basic of these forces, and this is gravitational force. Before we look at gravitational force in depth, I'd like you to understand that a force is usually exerted by something on something else. For example, in the previous discussion, I was talking about a situation whereby you may be pushing a box. That force is exerted by the person, and it is exerted on the box. Forces do not work in isolation. They work in such a way that you've got to mention what is applying this force and on what is the force being applied. So gravitational force is the force of attraction between two objects of given masses. Force of attraction. And the most common one that we think about is the force of attraction between the Earth and the Sun. And let's look at a simulation of the same. So here I've got the Sun. Let's switch on the simulation, and we can see that over here we've got the Earth, and it is moving around the Sun. Its path is circular. So let's just show that trace. There is something that I've got to activate here in order to show the trace. Yes, there. You will realize that. Let's just have it move normally. So its path around the Sun is circular. Without the presence of the gravitational force on the Earth by the Sun, our planet will not move like that. So at this point, we can be able to show the direction of this gravitational force. You see those two arrows there? This is what they mean. So let us pause the simulation and then I explain those arrows. This first arrow here that is pointing from the Sun to the Earth means this. The Earth is pulling the Sun towards itself. In other words, our Earth is pulling the Sun towards itself with a force which we indicate on the Sun. So this force is not produced by the Sun, it's produced by the Earth. The Earth is attracting the Sun towards itself. So again, you can see the rule. The force is applied by the Earth on the Sun. This other force here means the Sun is pulling the Earth towards itself with this amount of force. These two forces are usually equal in magnitude but different in direction. They actually act in opposite directions. And this is what I was talking about when I said forces acting in pairs, and the fact that when we mention forces, we must always state this force it's being applied by what agent and on what other object. So that one is an example of gravitational force. When we think about the Earth and the Moon, the same thing happens. The Moon usually moves around the Earth in a circular orbit. And again, you can see those blue arrows. They mean exactly what we've talked about. So these are forces, they are gravitational forces. Another type of gravitational force is a situation where we've got a satellite moving around the Earth. You can see that. Satellite moving around the Earth. Again, a gravitational force are the forces which enable these to happen. We will study more about these forces in other topics like Newton's laws of motion. For this lecture, we are just mentioning the types of force. Okay, I don't want you to always think that gravitational force only acts on large objects. Gravitational force also acts on us. It is the force which keeps us in contact with the Earth. If, for example, you jump upwards, that gravitational force quickly brings you down. So there is a force of attraction between these two objects, yourself and the Earth. And let me try to illustrate that on a diagram so that you can get the idea of actually what we are talking about here. So over here, I have this large sphere here. It is the Earth. The Earth has got a center here. And we might have a person here standing on the Earth, like that. So, the Earth is going to exert a force on this person towards the center of the Earth with this amount of force, and it's called gravitational force. And this person is also going to exert the same amount of force on the Earth with the same amount of gravitational force. This is where most students fail to understand. They fail to understand the significance of putting two arrows and why they should be pointing towards each other. Each one of the arrows means something different. This means the amount of force the Earth exerts on you so that when you jump upwards, it quickly brings you down, like that, or downwards. So, this gravitational force is the same force that we call weight. Weight. W, like that. Now, I want, from the very beginning, I want to discourage you from referring to this force as gravity. Many times when students are given this type of question, they talk about gravity. You ask them, name this type of force. They say gravity. No, don't say that. Because if you say that, it is synonymous. It is very close to talking about a different physical quantity, which we call gravitational field strength. Gravitational field strength, which is sometimes referred to as gravity. We say the gravity of the Earth and the gravity of the Moon, they are quite different. In fact, the exact term to use there is gravitational field strength of the Earth and the Moon. They are quite different. So desist from using the word gravity. Just refer to it by its correct name, gravitational force or weight. So this one is just a simple description of gravitational force, what it is. So here we've got the Earth and this particular person here. How about their masses? Their masses are like this. This one will be small mass. This one will be big mass. Now, this surface of the Earth here, in most cases, you expected me to draw a horizontal line like this, or to draw this person here. Remember, wherever you are on the surface of the Earth, that small ground that you are standing on, actually, at this point, it appears to be small, but in a real situation, it is expansive, it is very big, and it appears to be flat. It appears to be flat like this. And then you always stand like that. And to you, this appears upwards and this appears downwards. But do you know that a person on the other side of the planet, standing on the planet, also views this as being upwards and this as being downwards? Or on this other side of the same planet, here, this person here views this to be upwards and this to be downwards. So the concept of upwards and downwards is relative. It depends on where you are. What is upwards to you is not upwards to another person on the other side of the planet. It may appear to be downwards altogether. So over here, we will talk about the type of force which is acting on you. Let me use a different color. This one will be weight, W in short. And this is the amount of force that the earth exerts on you. And because that one is the most important force, we rarely talk about the amount of force that we are exerting on the earth towards ourselves, and that is the amount of force that we will be talking about. If you're talking about an object, maybe a box on the surface of the earth, the same type of force will be given. Now let's talk about the next type of force, which is reaction. So the second type of force that I want to talk about is action and reaction. Action and reaction. We could use the same situation. This time, I'm going to use a box on the floor here. The earth pulls this object downwards with a certain amount of force, which we have called gravitational force or weight. So remember, this force is not produced by this mass. It is the earth which is pulling it downwards. But this box does not move because it is in contact with a solid surface. So because it doesn't move, this solid surface exerts an amount of force on it in the opposite direction, which we call reaction, R. That reaction force is always at 90 degrees to the surface. You see, this is the surface. This is 90 degrees. That is why it is usually referred to as normal reaction. That's why it is referred to as normal reaction. Normal means 90 degrees. So you can regard this weight as this way. As far as the ground is concerned, this flow, it appears as if this object is exerting a force on the ground. But I've already explained where that force comes from. As far as the ground is concerned, it appears as if this object is exerting a force on the ground vertically downwards, although we know where it is coming from. Then the ground exerts an equal force to it in the opposite direction, which we are calling reaction. So the weight of the object may be regarded as the action, while the force that the flow exerts on the object is called reaction. So that is one way of looking at action and reaction. Another one would be something like this. Imagine this is the wall. There's wall here, and you may push the wall. Think about a simple diagram like that one. You are pushing the wall. The amount of force that you exert on the wall will be the action. That one will be the action. The wall does not move, so it exerts an equal force on you backwards, which we call reaction. An action and a reaction. So that force which is exerted on another one is usually referred to as the action, the first force to come into play. For example, you have deliberately decided to exert a force on the wall, and then the wall reacts to that. Action and a reaction. Let's look at another situation. We may have a situation where we've got a balloon. If you are allowed the air to come out of the balloon, you loosen the string so that it comes out with great amount of pressure. If you allow that to happen, the air will come out with a lot of force. That will be the action. That air that is coming out exerts an equal force on the balloon, and that is the reaction. So the action is the amount of force exerted by the balloon on the air, so that the air comes out with a lot of pressure. And then the air itself exerts an equal force on the balloon in the opposite direction, and that is what makes the balloon to fly around. And that concept is used in rockets. Again, action and reaction. Again, when you are standing on the floor, this weight, your weight, is the amount of force that you appear to exert on the floor. So as far as the floor is concerned, if it was a person, they would think that you are the one who is exerting that force on the floor. And therefore the floor reacts. In order to keep you in equilibrium, it must exert an equal force in the opposite direction to you. That's how you think about action and reaction. Other types of forces are also action and reaction types of force, and we are going to look at them presently in a moment. Let's just take a break and then we come back. Okay, welcome back. The next force that I want to talk about is frictional force. We are well aware that friction force can be important in our lives, and it can also cause a problem in our lives. Let's look at, for example, situations where it is necessary. And this one is when you are walking. So here, I'm going to attempt to draw the foot. This is the floor. It may not be a very accurate diagram, but just bear with me. It may just be something like that. This is the shoe. Something like that. That's it. And I just have very simple diagram like that. This person is moving forward like this, and you're asked to show the friction force between the foot and the floor. We define friction force as the force which opposes motion between two objects. And there is a tendency for students to think that friction force acting on that foot is backwards, is in the opposite direction to the direction the object is moving. But that is not the case. Let's think about the two forces which are acting in this situation. The first of this force is, you see this foot here? For you to be able to walk, you attempt to push the ground backwards. So there is this force that you push the ground backwards with, and we can call it the FD, like a driving force. It is your driving force. For you to walk, you have to push the ground backwards. And how do we know that you push the ground backwards? It's because if the floor is slippery, for example, if there is a lot of soap water on the floor and you try to walk, you find that you always fall. It's because there is very little friction force. You are attempting to push the floor backwards, but instead of there being friction is very, very small. So you find that the two surfaces are going to slide against each other. So we need to bring in friction so that we can prevent these two surfaces from sliding against each other. So the amount of force that you apply on the floor backwards acts like that. It is the action. The reaction to that is the force that the floor exerts on your foot in the opposite direction. And this force is what we call friction. And you can see we've been able to determine that friction actually acts in the same direction as the direction in which you are moving. It is not the other way around, what people think about. The friction force which tends to prevent you from, or slows you down, or tends to prevent you from moving is the friction force exerted on you by the air. And we call it air resistance. So air resistance will definitely tend to slow you down, tend to oppose the direction in which you are moving. Air resistance. But it's different from this friction force between your foot and the floor. So hopefully you've understood that particular situation. So friction force is a reaction, while FD, the driving force, is the action while you're moving in that particular direction. Let's look at a car, for example. Let me use this space here because I can see I've not used that slide. Let's just take this to be the road surface. Is the road surface. This is the one of the tires of the car. It's got 4 tires. Let's assume it is 4-wheel drive. Looks like that. Let me just draw simple diagram, and you can see these diagrams are very simple to draw. Okay, let's assume that there is a car that looks like that. And this is a driving tire. What does a driving tire do? The engine tends to turn the driving tire forward, clockwise. For example, here this tire tends to turn this way, but it's in contact with the road. So what the rubber surface of the tire does is to try to push the road backwards with a force we are calling the driving force. Of course, this driving force is not on one tire. It's in all the 4 tires. If, for example, this one is a 4-wheel drive car. But if it is not a 4-wheel drive and that the driving tires are this, then we concentrate on that part. But remember, whatever we are doing here is whatever we do to this one. So it tends to push the road backwards, and the road, you know, at that particular contact, you can think about it. It's trying to push the road backwards. The road surface reacts to that and pushes the tire forward with an amount of force we are calling friction. So this is friction. Again, action and reaction. And you can see, since this car is moving forward, there is a driving force which, as far as the tire is concerned, acts backwards at this particular surface. But as far as the whole car is concerned, then this driving force is acting forward like that. And then the bodywork of the car, there is air resistance. There is air resistance. Okay, so don't confuse the frictional force between the tire and the road surface with the friction force on the bodywork of the car by the air, which we call air resistance. They are quite different. And in most cases, when people think about friction, they think about the air resistance, and therefore they say it is opposing the motion, just because we have defined resistance to be that force which opposes motion between the two surfaces. Even here, it is opposing the motion between the two surfaces. Because in the absence of friction, this tire is just going to skid. Now, which other force is exerted by the tire on the road surface? The other force which exists in that situation is the gravitational force, the weight of the car. Of course, it is distributed on all the 4 tires. I'm just using a quarter of that force, because if the weight of the car is 1,000 newtons, for example, which is very, very small, that one's a toy car. It should be 15,000 newtons. Then about 7,500 newtons will be a quarter of that. Let's say 20,000 newtons. A quarter of that will be 5,000 will be exerted on this tire. Whichever the case, whatever I do here is what I will do here. So, this weight is the amount of force that the tire exerts downwards on the road. The other force that the tire exerts on the road, and notice that I'm very careful when I'm talking about what is exerting the force and on what. I'm talking about the forces exerted by the tire on the ground. There are 2 of them. This FD, which is a driving force, and this weight. We are going to see later on that when we add the 2, we are going to connect them head to tail. And this one and this one will be represented by one force which points in this direction. So if somebody asked you to show the one force, the total force that the tire exerts on the road, it is a combination of the driving force and the weight, and it should be in this direction. How about if I'm asked to show the forces which are exerted by the road on the tire? Of course, we know one of them. The other one should be the reaction. Remember, there is a reaction here. Normal reaction. Normal reaction. So, this normal reaction is the force exerted by the road surface on the tire. This friction force is the force exerted by the road surface on the tire. So, there are 2 forces exerted by the road surface on the tire. Again, I add them. When I add them head to tail, I'm going to get the one force which acts in this direction, which will be the one force which represents all the forces exerted by the road surface on the tire, and it is this way. And it will be opposite and equal in magnitude to this force. So here, there is a lot of understanding for you to be able to go through the video once again and see what I've said about each one of these forces. And you will never go wrong there. Now let's look at the next force, which is upthrust. Upthrust. So this force here is upthrust. There are 2 words here. Up meaning direction, thrust meaning force. So upthrust is a force. But sometimes you find that people talk about upthrust force, which is understood because in each one of these forces we are putting the word force at the end. frictional force, gravitational force, tension force. But if we just say upthrust, it is enough. This is the amount of force that a body which is immersed in a fluid experiences due to the liquid. The amount of upward force exerted on an object which is immersed in a fluid. This force will be studied more in Form 4 when we do the topic floating and sinking. But for now, we can just look at a simple situation whereby we've got a beaker of water there, and then we've got a string. There's an object there. It's supported on a spring balance. By the way, we forgot to state that the apparatus we use in the lab to measure force is referred to as a spring balance or a force meter. Force meter. Now we are going to take that object and immerse it in this water. So this was the initial level of the water. When we push this object inside, of course, one of the effects is that that surface of the water will rise. We know this from measurement 1, where we said the water is going to get displaced. But what we are interested in here is not this displaced water. No, it is this. This object here experiences two types of forces. One of them is its own weight, which is the gravitational force on it. The other one is the tension in the string. Okay, I will talk about tension later on. It will be the next force here. But think about this string pulling or supporting this mass. And it definitely must pull the object upwards. This tension is experienced by the spring here. So this spring balance is going to give us the tension in this string. Maybe let us say it's 100 newtons. That is the reading of the spring balance when it is in air. So this is the weight of the object in air, 100 newtons. When this object is weighed in water, so the weight of the object in water is certainly less. So it appears to weigh less. Why? Because the water has exerted a force on it vertically upwards, which we call upthrust, which is this one here, upthrust. But the tension still exists. Remember that tension is now 80 newtons. The weight of the object is still there, 100 newtons. The difference is the upward force, is the upthrust. So upthrust is usually calculated like this. You can say that the sum of upward forces, which is tension plus upwards plus upthrust, is equal to the weight of the object in air. Like that. When you rearrange, the tension here is 80 newtons. The weight in air is 100 newtons. You see, this tension here, let me just clarify a few things because I want you to get this one straight. This tension, forget about this tension. This tension is 100 newtons, and it is equal to the weight of the object in air, which is 100 newtons. This tension here is also equal to the weight of the object in water, which is 80 newtons, because the reading of the spring balance gives us the tension in the string. So the tension I'm referring to here is this one. So if we were to rewrite this equation properly, this it's just appropriate that we call it weight in water. Weight in water, this is weight in air. And you can be able to say that our upthrust will be equal to 100 minus 80, which is 20 newtons. Like I said, this topic will be dealt with in Form 4 under floating and sinking. Now let me quickly go through tension. Okay, where do we get tension? We get tension mostly from springs. This one is the support of a spring. Got a spring which is hanging there. It's common knowledge that if we are to suspend a mass there, that spring will become longer. It will stretch. It will extend. It's because this mass pulls it downwards with a force equal to its own weight. And then this spring pulls it upwards with a force equal to tension in the string or in the spring. The same spring pulls this support downwards with a force equal to tension in the spring. So tension in a stretched body is represented by two arrows which point towards each other. But those two arrows have got different meanings altogether. And I've already explained this. This tension in the spring, it is the amount of force that the spring exerts on this body, because it's the one which is trying to pull it upwards and therefore supporting it. So the amount of force it is applying is a pull. It's a pull. So that arrow should point away from the body. Remember when we just did? This one is a pull. This one is a push. So over here, this spring is pulling this body upwards. And that is why this arrow is pointing away from the body. The same spring is pulling this support of the clamp downwards. Another example that we can think about is a situation where we've got a piece of thread. Sorry, it should be straight, piece of thread, and this object here, the one that I've used in the study of upthrust. So one of the forces exerted on this body is the weight. One of the forces exerted on this string by this body is the weight of the object. So if the weight of the object is 100 newtons, the string must support it. It must pull it upwards with the same amount of force equal to the tension, called tension, and it should be equal to the weight of that body. The same string pulls the support downwards with a force equal to tension, which is 100 newtons. So if this string was tied to a spring balance, that string will pull the hook of the spring balance with a force equal to 100 newtons, and the spring balance will tell us how much force has been exerted on it. That is why we say the spring balance is used to measure force. And those are the forces that I wanted to talk about at the moment. Next, I'm going to talk about cohesive and adhesive forces. Okay, what are cohesive and adhesive forces? Before we go very far into that, or before we even get started, there's a diagram that I've seen in your course book which I want to draw your attention to, and it is the one where you can be able to determine the upthrust acting on an object. So the first thing you do, you measure the weight of the object in air using a spring balance as shown, and then you put some water in a beaker. You immerse the object in the beaker, and you will make the two observations: that the level of the water in the beaker is going to rise slightly, because of the volume of the water which is displaced as it gives way for the volume of the solid which has just come in. The other observation you will make is that the reading of the spring balance will be less compared to the reading of the spring balance in air. So we refer to this weight of the object in air as just that, weight of the object in air. And then when it is immersed, we refer to it as weight of the object in the fluid, in water, for instance. And then you can even change the liquid that you are using. What type of observations are you going to make, given that paraffin has got a lower density compared to water? That may be an investigation you might want to carry out. And if you find that the weight of the solid when it is immersed in paraffin is less compared to the weight of the solid when it is immersed in water, then I will challenge you to do further investigation and give an explanation to that. However, let's go straight to cohesive and adhesive forces. Again, in the same course book, I'd like you to read on cohesive and adhesive forces because it is clearly written there. The forces of attraction between molecules of the same kind, they are what we are referring to as cohesive forces, while the forces of attraction between molecules of different kinds are what we are referring to as adhesive forces. Now, what do we mean by molecules of the same kind? We are talking about a water molecule and another water molecule attracting each other. What do we mean when we say molecules of different kind? We mean a water molecule and a glass molecule. Now, this kind of these two forces are responsible for the following observations. If you get a clean glass surface, two glass surfaces, one of them is clean, the other one is not so clean. You can put some Vaseline on it or some grease on it in order to make sure that it is not clean. The other one is washed thoroughly in soap water and then dried, so it is clean. And then you get a drop of water. You put a drop of water on each one of those surfaces. What are you likely to observe? You will observe that the surface, where the surface of the glass is clean, that water drop is going to spread. But where the surface of the glass is greased, it's dirty, the water is going to form droplets. What kind of explanation can we give here? It is the relative sizes of the two forces involved. Remember, in each one of them, the two forces are involved. Cohesive forces between water molecules and adhesive forces between water molecules and glass molecules. On a clean glass surface, when the drop spreads, it means that the adhesive forces, the forces of attraction between glass molecules and water molecules, is greater than the cohesive forces between the water molecules. So we are going to have more water molecules wanting to be in contact with the glass, and that is why the drop spreads. On the other hand, on a dirty glass surface where the water drops are going to be spherical, it is the other way around. The cohesive forces, the adhesive forces have been reduced significantly. The adhesive forces between glass molecules and the water molecules have been reduced in such a way that now cohesive forces are stronger than the adhesive forces. So remember, it is the adhesive forces that have been reduced when you make the surface of the glass to be dirty. The same observation can be made when we have water and mercury. The two glass surfaces, we can make them to be, on average, they should be clean. You'll find that the water will spread, but the mercury is going to form spherical drops. Like, for example, in this diagram here, you will discover that here, the cohesive forces in mercury, they are very, very strong compared to adhesive forces between mercury and glass. While for water, which spreads, the water spreads, or we say it wets the glass, the adhesive forces between water molecules and glass molecules is greater than the cohesive forces between water molecules. And that is what we can say about those two types of forces. So all the time, they'll bring us that kind of question. Sometimes they can bring us this question and ask us this question. When you look at the surface of the, let me zoom in into this diagram so that we are able to see details of what is happening. Let me put away the navigation of this book. By the way, when you go to the video description of this video, you may find that I've put a download of this textbook so that you can be able to study it at your own convenience. When you're using it, on the left hand side there will be a navigation, the one that I've just put away, you know, this arrow. You can be able to activate it. I click on it and there will be this watermark symbol there. If you click on it, it is going to reveal this navigation here, and this one is like that's like book 1. There is book 2, book 3, and book 4. It's quite a big PDF. Even at the end of the PDF, I've put these Kcse examination questions, and they are arranged in a topical manner. Like for example, when we go to force, you will find the questions that I'm talking about. You will be able to see them there and be able to practice. So make sure you go to the video description and download the book. The other thing that I'd like to just to alert you on is if you're not a member of my channel, please consider becoming a member of my channel, because that way you get to know when I'm releasing new materials. It's also good for the rating of my channel and so forth. You realize that there is a lot of good things which I'm giving you in this particular channel. So it's always good to reciprocate and just subscribe. And it won't cost you anything by subscription. So let me again, zoom in, because I was looking at these two levels of two tubes. They are of, there is a wider tube, there is a thin tube. And look at the surface of water in this tube. The reason why the surface of the water always curves upwards like that is because of the strong adhesive forces between a glass and water molecules. And the reason why mercury usually forms dome shape like this, curved downwards, is because of the strong cohesive forces compared to the adhesive forces. So here the cohesive forces are stronger than the adhesive forces. Here the adhesive forces are stronger than the cohesive forces, and hence what you see. So more water molecules would want to come into contact with the inside part of the tubing. So for that force to support a certain water column, you'll find that when the tube is thinner, then the length of that water column is going to be greater. You can see that it runs all the way up to this point. That one is going to be greater because more water molecules have got to be in contact with the glass surface. The opposite is true. If you put a thin tube in mercury, it will sink much to a much bigger distance compared to this one here. So go right ahead and you'll be able to read the explanation there. The explanation is so clear. Let's go through it together. The level of the water inside the tube is higher than that outside the tubes. This is for water. tubes put in water. A meniscus is formed at the top of the water level. The water curves upwards from the reading level, that is concave. The rise in the tube with a smaller bore is higher than in the tube with a larger bore. Should always be able to make that observation, because sometimes in some of these questions they just ask you to indicate those levels. Different liquids rise by different heights depending on the diameter of the glass tube. If mercury is used, the level of mercury inside the tube goes lower than that outside the tubes. Be careful about that, because you can be given a situation whereby you're comparing water and mercury. You should be very careful. The surface of the mercury in the tubes will curve downwards. That is, the meniscus curves downwards from the reading level, that is convex. The level of mercury in the tube with a smaller bore will be lower than that in the tube with a larger bore. These are the observations. How about the explanations? Again, the explanations are given very, very well there. Get the habit of reading the textbook and trying to get some of these materials from there. Since the adhesive forces between water and glass molecules is greater than the cohesive forces between water molecules, the water rises up the tube. The adhesive forces between water and glass molecules greater than the cohesive forces. That is why the water rises up the tube, so that more water molecules can be in contact with the glass, so that we can have more water molecules being in contact with the glass. So as the water tends to fulfill that situation or that condition, it ends up rising up the tube. Of course, we say that this wets the glass. Liquids such as glycerol, kerosene, and methylated spirit wet the glass or the vessel and will rise in a narrow tube. Let's look at for mercury. On the other hand, the forces of cohesion within mercury is greater than the forces of adhesion between mercury and glass. Again, I've already explained that. Further explanation is given there. These are some of the details that you remember, that you'll want to remember. The mercury therefore sinks down the tube to enable mercury molecules to keep to themselves. When it was water, it is to enable more water molecules to be in contact with the glass surface. But here, it is for more mercury molecules to keep together. Liquids which do not wet the container will be depressed inside the tube. And of course, mercury is about the only liquid which behaves that way. So that is what we can say about cohesion and adhesive forces. The other type of force that we'd like to study here is surface tension. You know, a situation whereby the surface of the liquid behaves as if it is under tension, or as if there is an elastic skin on the surface of the liquid. And there are several experiments we can be able to do. If you get some water in a glass and you fill it almost all the way to close to the brim, and then you carefully put a needle on it, a pin, you know, the office pin, the normal office pin, carefully put it on the surface, you will be able to observe. If you use a lens and look at the surface very closely, you'll be able to observe that the water is depressed. Around at the bottom of the pin, it is depressed. Why is that? It's because the surface of the water molecule behaves as if it is under tension. So let me go straight to that, and then I show you exactly where to read in your textbook. It's important when you get this textbook, read it. So this is the experiment I'm talking about to investigate the behavior of a liquid surface. So this is the pin that we have carefully put on the surface of the water. When you look at it carefully, you will see that it will be depressed. Here it doesn't show very well, so let me draw it for you. So this is what we have here. This will be the pin, the cross section of the pin. When you look at the surface of the water, it will be like this. It will be depressed here and then like that. The forces acting is one of these will be the weight of the pin, and then there will be these cohesive forces here, surface tension. Then this plus this will give rise to a force which supports that pin, and that is what you have in the textbook. Let's look at the textbook and see. This is what you have. The surface tension, the two forces, this one and this one, gives a rise to a resultant force upwards like that, which tends to support the weight of the pin. So there are several effects of this. Of course, after you do that experiment, the following observation is expected. The needle floats on the surface of the water and remains floating so long as the water surface is not broken. Should be careful not to break the water surface. Especially, don't just drop the pin. It's got to be suspended very careful. When the surface of the water where the needle lies is observed carefully, a magnifying glass would help. So use a magnifying glass to look at that. The water surface is found to be slightly depressed and stretched like an elastic skin. And this is where we get the definition of surface tension, where the surface of the liquid behaves like a stretched elastic skin. That shows there is surface tension. Now, how can we reduce surface tension? We can use impurities. One of these is by using soap or increasing the temperature. Let's see what you can be able to do in the lab in order to achieve this. When drops of paraffin or soap solution are put on the surface of the water around the needle sinks on its own after a few seconds. If alternatively the tip of the needle is depressed slightly into the water, it's going to break that surface tension. The needle sinks very quickly to the bottom of the water. Let's look at the explanation. The steel needle or the razor blade floats because the surface of the water behaves like a fully stretched, thin, elastic skin. Fully stretched, thin, elastic skin, like that one of a balloon. This skin always has a tendency to shrink. It behaves like a spring that has been stretched. Okay? If you release the ends of the spring that has been stretched, it always shrinks back. That is to have a minimum surface area or elastic membrane. It wants to have the smallest surface area. And that is why liquids always form drops. They form drops because a large volume of the liquid can be contained in a spherical shape as compared to any other shape. So spheres have got the smallest surface area, and therefore they can carry a lot of water, a lot of the liquid, for example. Think about 1 centimeter cubed of water in a spherical shape and 1 centimeter cubed of water in any other shape, such as a cube or maybe even a cylinder. You'll find that the cube or the cylinder, the surface areas of those shapes is much bigger than the surface area of the sphere. So the reason why liquids form spherical shapes is because the surface of the liquid behaves like a fully stretched elastic skin, which tends to achieve the smallest possible surface area. And the spheres have got the smallest surface area. So let's continue. So we have already said that this skin always has a tendency to shrink, that is, to have a minimum surface area or elastic membrane. The force which causes the surface of a liquid to behave like a stretched elastic skin is called surface tension. They always ask us to describe surface tension. This force is due to the force of attraction between individual molecules of the liquid, cohesive forces. So cohesion, we studied it under cohesive and adhesive forces, but we can go further and look at the causes of surface tension, and it comes from the forces of attraction between molecules of the same kind. Let's look at molecules which are on the surface of the liquid. So again, I'm going to use, let me use this space here. You can think about this being the surface of the liquid, and there is a molecule here. There is another molecule here on the surface of the liquid, and there is one which is inside the liquid. The one which is at the surface of the sphere experiences these forces. It will be pulled by this one. This one will also pull it. The other one will pull it like that. It will also be pulled by the molecule inside the liquid. This is what happens to the molecule at the surface. It doesn't have any other force up there trying to pull it that way. Then this one will be pulled by this molecule this way. Of course, this force is the amount of force exerted on this molecule by this one. So it's going to be pulled downwards. Therefore, over here, these molecules always will be under tension at the surface. They are always trying to achieve the smallest possible surface. Why? There is no force which is pulling it in the opposite direction. But the one which is in the liquid, it's pulled in all directions with the same amount of force. So it is not, there is no resultant force on it. We'll talk about that concept of the resultant force in a moment. So here we are looking at the explanation why the sharp, when we prick the surface of the liquid with either, you can get a needle, then you heat it in a flame, and then you come and put it on the surface of the water. As it cools down, it's going to break the surface tension. The needle or the blade sinks when a drop of kerosene or soap solution is put in the liquid near the needle, because kerosene or soap, being an impurity, reduces the surface tension of the water. When the tip of the needle is pressed into the water, it pierces the surface skin and sinks. You know, the moment it pierces the skin, then the surface tension is broken. It's like when you have a stretched spring and then you cut it at the center, the ends are going to jump in opposite directions. And of course, I've already explained this. So remember, you can be able to use cohesive forces, that is forces of attraction between molecules of the same kind, to explain surface tension. And the explanation is given there. So go right ahead and read that situation. Another demonstration that you can carry out in the lab to demonstrate surface tension is by using a funnel, a glass funnel. Get some soap solution, put it in a large beaker, put the funnel in, and then lift the funnel out. The moment you do that, there will be a film that will be hanging on the other end here. You can blow on this other end using your mouth. Of course, be careful that the soap doesn't get into your mouth. Just blow out the air, and you'll be able to see that this bubble becomes bigger and bigger and bigger. And then at some point, you stop blowing and observe what will happen to this bubble. It will start to shrink inwards, shrink like that. And then when it reaches this point, it stops moving. You know, remember that surface tension tries to make the surface of the liquid to achieve the smallest ever surface area. The reason why this soap bubble shrinks upwards like that is in an attempt to achieve the smallest surface area. The moment it reaches this point, then it doesn't move any further because the surface area at this point is equal to the surface area at that point. Again, the observations and the explanations are given. And there is also another one about a loop of wire. You could get a loop of wire like this, put a string at the center, which is loose enough, and then dip the whole of that in soap water, and then lift it out. And then using, you can even use something like even your finger, you can touch now this point here. When you touch this point, you're going to break the surface. When you break the surface, the string quickly forms this perfect curve like that, meaning that the string is being pulled normally to the surface, okay, showing that there exists this remaining film has got tension in it. Tension, there is tension in it. It tends to pull whatever is there towards the other molecules. So that is a good example of surface tension. Another one that is possible is by watching the mouth of the tap, and you open the tap very slowly. You will see a drop start to grow. The drop starts here, and as the water increases, the drop becomes larger and larger, more spherical. Like this, it elongates until eventually, when the weight of the drop is so big, it just drops. And we have a drop of water. Why does water form drops? We have already talked about that. And then finally, there is the glass tumbler. Fill it all the way to the top, almost to the brim, and you'll be able to see that the surface of the water actually forms something like this. Okay, and then you can do several things like drop a soap solution on it and see exactly what happens. And then even for the brushes, you will see the bristles of a painting brush, like the one that is used by art students. When you put it in the water, the bristles are all spread out. But the moment you lift it out of the water, then they come closer together. It's because the cohesive forces between molecules of water, as the water molecules trying to come together, they pull the bristles closer together. And this is what you end up having. Finally, there are factors which affecting surface tension, and there are two of them: impurities and temperature. You'll find that when you introduce impurities into a liquid, you lower the surface tension. When you raise the temperature of the liquid, again, you lower the surface tension, and the factors are given there. Impurities reduce surface tension, that is, presence of impurities reduce surface tension, and that is the reason why we use detergents for washing clothes. Detergents, for instance, weaken the cohesive forces between liquid molecules, and you find that the surface tension consequently is reduced. Temperature. With the rise in temperature, the kinetic energy of the molecules of the liquid is increased, and the intermolecular distances increase, and the forces of cohesion is decreased. Because as these molecules are moving faster and faster after absorbing heat energy, they are going to move away from each other, and that is going to reduce the forces of attraction between those molecules. Again, surface tension reduces. The most important thing here is to know how the impurities and temperature affect surface tension. Read about the consequences of surface tension. We have already talked about action and reaction forces. So again, read about that. Let me briefly talk about weight and mass. Now, at the beginning of your study in physics, you encountered the basic physical quantities, and one of them was mass. Mass. It is a basic physical quantity. Weight, on the other hand, is a type of force. We have already talked about the gravitational force, and we have said gravitational force is the amount of forces of attraction between two objects of different masses. So we might have a surface here. Let me just repeat that because it's important. This mass will be pulled by the earth downwards like that with a force we call gravitational force, or as far as this surface is concerned, we can say that this object exerts a force on this surface called weight of the object. But this object here has got another measurable feature, which is mass. You can take a beam balance find the mass of the object there, find its mass in grams. Maybe you're going to find that maybe this one is 75 grams, for instance. Get the same object, measure its weight using a spring balance. The same object, measure its weight using a spring balance, and you'll find that its weight is 0.75 newtons. Repeat this procedure with several objects, whereby you start by measuring the mass in grams, then you convert that mass in grams to mass in kilograms, and then measure the weight of the object using a spring balance in newtons. Then go ahead and calculate, divide that weight by the mass to get a new physical quantity which we call gravitational field strength. Its unit will be Newton per kilogram, because we know weight is in newtons, mass is in kilograms. Do this with several objects, different objects. You will discover that this ratio is approximately 10. It does not matter the kind of mass, how big or how small it is, you'll get a constant value. This constant value is what we call the gravitational field strength of that planet. In this case, it will be the gravitational field strength of the Earth. And this is what many students, when they are talking about, instead of talking about the weight of an object, they talk about gravity. When you talk about gravity, you are talking about a constant value, which is this one here, gravity. And in fact, its actual name is gravitational field strength of the Earth. What this means, because the gravitational field strength at a point closer to the Earth's surface is 10 Newton per kilogram, what this means is that the gravitational field exerts a force of 10 newtons on a mass of 1 kg. The gravitational field of the Earth exerts a force of 10 newtons on a mass of 1 kg. This is the gravitational field strength of the Earth. We are told that the gravitational field strength of the moon is 1.67 Newton per kilogram. Again, what this means is that the gravitational field of the moon exerts a force of 1.67 newtons on 1 kg mass put in that gravitational field at that point. So the moon has got a smaller gravitational field strength compared to the Earth. So what happens Okay, according to this equation here, you can write W being the subject, and you can see that it's going to be equal to mass times G. So if you have a mass of 2 kilograms on Earth, its weight will be 20 newtons. Don't confuse mass and weight. Remember, weight is a force, mass is a basic physical quantity, which is actually a scalar quantity. I'm going to mention that pretty soon. Weight is the gravitational force on an object, or the amount of gravitational force exerted by the planet on the object, while mass is the quantity of matter in the object. That is a clear distinction between the two. This brings me to this point. When you're asked to distinguish between two things, they are asking you to state clearly what is distinct between them. And in order to bring out a very good distinction, always say what they are in terms of defining them. So if you ask to distinguish between weight and mass, just give the definition of each one of them. Of course, we know there are differences. There are differences out there. Don't confuse this question. Differentiate between mass and weight. You can talk about so many things which are different. When you are asked to distinguish between them, you are being asked to state what they are, what each one of them is, how each one of them is defined. So let's look at some of the information in your textbook. Here you have that experiment that I've just described that you can be able to do and come up with that relationship. There is a table that shows the differences between them. Let's look at the first one. It is the quantity of matter in a body, that is how mass is defined. It is the pull of gravity on a body. It is the amount of gravitational force on the body. I've given you a clear definition on that. So you can see even our textbooks sometimes they make mistakes. Pull of gravity on a body. A better way of putting it, definitely it is the amount of gravitational force on that body. That first difference is what you should state when you are asked to distinguish between mass and weight. Other differences include it is measured in kilograms, that is mass is measured in kilograms, weight is measured in newtons. Mass, this one is important. The mass is the same everywhere, but weight changes from place to place. Now let me illustrate this by what I've just calculated. The weight of a 2 kg mass on Earth is 2 kilograms. And then I multiply by 10 Newton per kilogram. And I find it is 20 newtons. So on Earth, let me take this object to the moon and determine its weight. Again, it's 2 kilograms. Weight does not change. I mean, the mass of an object does not change. However, on the moon, the value of the gravitational field strength is 1.67 kilograms. I mean, Newton per kilogram. Sorry for that mistake. So Newton per kilogram. And you should be able to see this one should give you this times 2 is 14. This one will be 13. This one will be 3 kilograms. I mean newtons. So you can see on one place the weight of an object is 20 newtons. On a different place the weight of the same object is different. So it's clear weight changes from place to place while mass remains the same. Why is that? Weight changes from place to place because the value of the gravitational field strength changes from place to place. That is the reason. But mass does not change because the quantity of matter in it does not change. The number of particles in it does not change. The mass of each particle in it does not change. That's why mass does not change. The number of particles in it does not change, and the size of each particle does not change. That is the reason why mass remains the same. Other differences include weight is measured using a beam balance. Mass is measured using a beam balance. Weight is measured using a spring balance. It has magnitude, that is mass, but weight has both magnitude and direction. Okay, at this point, I'd like you to go through this question here where you're given an astronaut weighs 900 newtons on Earth. On the moon, he weighs 150 newtons. Calculate the moon's gravitational field strength. Given that G is equals to 10 newton per kilogram on Earth, this is the G due to the Earth. So I expect you to be able to calculate the mass of the object and then use that mass on the moon to find the gravitational field strength on the moon. Now, that point there brings me to measurement of force. I've already mentioned how we measure forces. I want to go straight to the vector nature of forces. Now, I've already mentioned about the vector nature of a force. A vector is a physical quantity which has got magnitude, which is represented by the length of this arrow, and it has direction. That is what a vector is. And weight, being a force, is a vector, and mass is a scalar. A scalar is a physical quantity which has got magnitude only. So that is the first thing you should know about vectors and scalars, how each one of them is defined. A scalar is a physical quantity which has got magnitude only, that is a number and a unit only. But a vector has got both magnitude, that is size, and direction. So let's see how when we are given an object, see this object here, it has a force of maybe 5 newtons and another force of 2 newtons applied on it. This is similar to having a force of 5 newtons. This is like 5 centimeters. You add 2 centimeters, you get 7 centimeters. And if you're using 1 centimeter to represent 1 newton, then 7 centimeters is 7 newtons. If on the other hand you had the same object with a force of 5 newtons exerted that way and a force of 2 newtons this way, you will follow the same method. You'll say, I've got this one here. Then I'll bring the tail, the tail of this one onto the head of this one. Just like I connected them head to tail, here I'm also connecting them head to tail. And then finally, this is what I get. I end up, it's like I'm starting from here, moving all the way up to this point. I find that if this is 5 centimeters, this is 2 centimeters, then this is 3 centimeters, which is 3 newtons to the right. 3 newtons is the resultant force. What is the resultant force? Resultant force is that single force which represents several forces acting on the object, or it is a sum of all the forces acting on the object. So the resultant force may, although we call it sum, may not be calculated the way we add numbers. Notice that here it's clear that 5 plus 2 is 7, but here 5 plus 2 is not 7. By the way, this is 2 newtons. 5 plus 2 is not 7. It becomes 3. How is that possible? It's because the resultant force is obtained this way. you will look for the bigger force. If they're acting in opposite directions, look for the bigger force, subtract the smaller one, and the direction of the resultant force is in the direction of the initial bigger force. I'm going to repeat this. Given two forces of different magnitudes and they're acting in opposite directions, subtract the smaller one from the bigger one, and whatever you get will be in the direction of the initial bigger force. For instance, the 3 newtons is in the direction of the 5 Newton force. Now, let's go ahead and look at a situation where the two forces are equal. I've got 4 newtons acting this way, and again, 4 newtons acting in opposite direction. Here, the resultant force, F resultant, is 0. We say the system is in equilibrium. This is one of the conditions for a system to be in equilibrium. The resultant force must be 0. So this is what I want you to do with this kind of information on this last section. Go to the exercise at the end of the chapter, exercise 3.3 in your course book, and then do the problems which are there that pertains to addition of forces or to calculating a resultant force or on an object. At this level, the type of forces you will be given to find the resultant force will be, they will either be in the same direction, in which case you will just add the 2, or in opposite directions, in which case you subtract the smaller one from the bigger one. And if the 2 acting in opposite directions have got the same magnitude, the resultant is 0. And that brings us to the end of this chapter. Go through each question. You can go through the timestamps that I've put on the video and be able now to skip to the question of your choice where you did not understand. After you've done that, in the video description, I have an exercise there that you can be able to download in order to test yourself whether you've been able to understand the concepts that I've been able to take you through in this very long video. Otherwise, I want to thank you for being patient in this video. I've decided to be giving these long videos so that you can really concentrate on a given topic. The next topic that I'll be talking about will be pressure. Don't forget to subscribe to my channel if you're not a member of my channel. And if by chance you find these videos useful, go ahead and share them with your friends. Your friends may be able to see something different from the way you are seeing it. And by discussing what you see in this particular video, you are able to understand these materials much better. So go right ahead, subscribe if this is your first time in this particular channel. Otherwise, see you in the next video, and remember to work hard. Bye-bye.